At the heart of every data center serving an AI model, whether it's a language model like Gemini and Claude, an image generator like Midjourney, or a video generator like Sora, is a GPU or a TPU, a graphics processing unit or a Tensor processing unit. And in this video, we're going to see how they work. A typical AI accelerator like NVIDIA's H100 is built from 80 billion nanoscopic transistors, wired together into 16,896 CUDA cores and 528 Tensor cores, capable of 2,000 trillion operations per second. Essentially the engine behind the entire AI boom. Compare that to the Google's TPU V5e, built from 4 grids of 16,384 multiply and add units, each wired directly to its neighbor with no memory in between. Capable of nearly 200 trillion operations a second, it does the same math a GPU does with less electricity on a cheaper silicon. Despite these two chips being built on opposite philosophies, they're both racing through the exact same calculation, multiplying grids of numbers trillions of times over. For every word the chatbot writes, every pixel an image model generates, and every frame of AI video. So before we open up these chips, let's look into that one calculation, because by the end of this video you will see why betting on it costs billions. When you type something into a large language model like Claude, you see the answers come back to you one word at a time. That's because they're all built on the same architecture called the transformer. A transformer takes an input and turns it into a different form of output. For a large language model, that input is a piece of text. Based on that text, the model gives back a list of words that might come next, each one with a probability. So every time it runs, one of those words gets picked. That word is added to the end of the text you gave it, and the whole thing goes back to the model as a new input, and it runs it again to produce the next word. Each word is also sent to you as it's picked, and that's what you see appearing on your screen. You've all seen the famous neural network graph that is used to visualize these models. It's made of layers of neuron, and every neuron is connected to the neuron in the next layer. Sitting on each one of those connections is a single number called a weight. These numbers get tuned during training before the model is released. The input is fed from the left into the first layer. Every neuron in that layer produces a number, and those numbers become the input to the next layer. That repeats layers by layer until you reach the last neurons on the right, and that's the output of the network. So in a sense, getting from an input to the output means doing one small calculation at every neuron layer after layer. In a real model, that's thousands of numbers going in, tens of thousands coming out, and billions or trillions of weights in between. Each one of these weights is what we call a parameter. Claude outputs is estimated to have around 5 trillion of these parameters. And as you can imagine, the more parameters the model has, the more calculation it takes to get to the output. The reason this network is drawn as a graph is to make it easier for us humans to visualize and understand. What the computer actually sees is a file of numbers on the disk, and those numbers are the weights or parameters of the model. These parameters are grouped together into matrices. A matrix is a grid of numbers arranged into rows and columns. For one layer, each row of the grid is one neuron, and each column is one of the neurons from the layer before. So the number in row 3, column 5 is the weight of the connection between neuron 5 and neuron 3. That's the reason a matrix is used to hold these numbers. The position of each weight in the grid does the labeling for us. A large language model is nothing but a set of these matrices. For example, in case of GPT-3 with 175 billion parameters, it consists of just under 28,000 of these matrices. To be able to interact with the model, these matrices are loaded into computer's memory. Then to feed your text into these layers of matrices and do the calculations, the text is translated into a set of matrices. After the calculation on all of the layers are done and we reach the last layer, the output of the network is also a set of matrices. That's then translated back into a list of words and the probability of each word for you to be able to read it. So what exactly are these calculations? When you run a large language model, almost all of these calculations are matrix multiplications. We are multiplying two matrices together. Here's what it looks like. You take the blue row, which is one neuron, and the red column, which is the input. You multiply the numbers in the blue row and the red column together in pairs and add the results. The resulting number goes where the blue row and the red column cross. Then the red column moves one to the right, and you do it again. When there are no columns left, the blue row goes to the next neuron, until every cell of the result is filled in. While we go through this, I want you to notice something. Every cell of the result matrix only needs one row and one column from two matrices we're multiplying. Calculating one cell of the result has nothing to do with calculating the other one. In other words, we don't need the answer from the first calculation to do the second one or the other way around. The order I walk you through, left to right and then top to bottom, was my choice, not a requirement. Thanks to this, we could do the calculation for all of the cells all at once, all together, and the result would come out the same. The reason we might want to run this matrix multiplication all at once or in parallel is that we want to get to the final final result faster. Take Claude Opus with its 5 trillion parameters. To produce one word, we need to do around 10 trillion multiply and add operations. So naturally it would be a lot faster if you can divide the result matrices into multiple parts and calculate all of those parts all at the same time. For example, if we split it, say 100 parts, it should take us 100 times less time to get to the result. To do this, we need multiple processing cores that work in parallel. The more of them, the better. And that's where GPUs and TPUs come into play. Graphics processing units and tensor processing units. Both of them are built with thousands of processing cores, which makes them the perfect machines for running these models. NVIDIA's H100 GPU comes with nearly 17,000 of these cores. The H100 is the GPU that the entire AI boom was built on. Almost every major language model you've used in the last 2 years was trained on a cluster of these. But now let's open up this card and see how it works. By the way, the H100 ships in 2 forms. Here's I'm describing the server module, which is the faster of 2. At the center of the card is the printed circuit board or PCB, with all of the components mounted on it. The first component we look at is graphics processing unit or GPU. When we open it up, we find a large silicon chip codenamed GH100, which is built with 80 billion transistors. Most of the GH100 chip's area is taken by processing cores, which are organized into groups and subgroups. This chip is split into 8 graphics processing clusters or GPCs, which collectively contain 132 streaming multiprocessor or SMs. Going deeper, each SM is equipped with 4 warp schedulers. Each individual scheduler manages 32 CUDA cores and 1 Tensor core. Across the entire GPU, this adds up to 16,896 CUDA cores and 528 Tensor cores working in parallel. Together, these cores power all of the GPU's computations, but they have different jobs. CUDA cores are flexible, general-purpose processors that handle standard math operations. Tensor cores, by contrast, are built explicitly for matrix multiplication and addition, the exact operation we just walked through. Inside each of these CUDA cores is a specialized unit that does a single multiply and add calculation, exactly what we did along the blue row, 1 pair at a time. Each core finishes one multiply and add every clock cycle. On NVIDIA's H100, the clock ticks 1.98 billion times a second. Because the chips pack 16,896 CUDA cores all working at the same time, it finishes about 33 trillions of these multiply and adds every second. And because the multiply and add count as 2 floating point operation, that's the 67 teraflops you see on the spec sheet. A Tensor core takes a huge step further. Instead of processing numbers 1 pair at a time like a CUDA core, it takes the whole blocks of the 2 matrices and multiplies and adds them in a single instruction. Now let's zoom out and look at the rest of the GH100 chip. Inside each streaming multiprocessor, there are 256 KB of registers, a tiny bit of ultra-fast local storage where a core keeps the numbers it's working on at that moment. Next to that is up to 228 KB of shared memory, which allows all of the cores inside the same multiprocessor to swap data if the code tells them to. Looking around the edges of the chip, you have the PCIe interface, which connects the card to the rest of the computer. Right alongside it are the NVLink controllers. This allows multiple cards inside the same computer to talk directly to each other, pooling their powers to run massive AI models together. Finally, down at the bottom is the gigathread engine, which sends each part of the calculation to whichever streaming multiprocessor that is ready for it. Now, aside from the graphics processing unit itself, perhaps the most important components are the memory chips sitting next to it. These are 80 GB of high bandwidth memory or HBM built by stacking DRAM chips into tall blocks. This is where the parameters of the models are loaded while the card is running. All of these stacks together can feed the chip 3.35 terabytes of data every second. That number is called the bandwidth and is arguably the most important spec on the entire card. After all, thousands of processing core can only work as fast as memory can supply them with data. To power all of this, the card drives 700 watts, roughly the same as 10 laptops running at the same time. Now let's actually run a model on this card. The card can't do anything on its own. It's a device connected to computer with a PCIe interface, and the computer is the one giving the instructions. The computer is called the host and the card is called the device. Every instruction starts on the host and every calculation happens on the device. Now, the model is the file of numbers on the computer's disk. For example here, let's take a model small enough to fit it on a single card's memory, say a 26 GB model. Each parameter is stored in 2 bytes, so a 26 GB file is about 13 billion parameters. The computer reads this 26 GB model from the disk and pushes it down the PCIe interface to the card's high bandwidth memory. The 26 GB cross over the PCIe interface and sit in the card's memory. And that's what it means when someone says a model is loaded. It simply means it's loaded into the card's memory. The model's parameters stays on the card as long as we're serving the model. Then when your text arrives, it's translated into matrices and then goes down the same PCIe interface into the same high bandwidth memory and sits next to the model. Now the card has everything it needs to perform the calculations. The matrix multiplication itself is a function instructed by the host and executed on the card. This kind of function is called a kernel. Alongside sending the kernel instruction to the card, the host also says how many workers this job needs to be split into. In other words, how many workers should be involved in running this job. For our example here, we're going to take the simplest way you can split a matrix multiplication between workers, which is when we assign calculating every cell of the resulting matrix to one worker. This isn't how a fast kernel actually does it, but it's the clearest way to watch what the hardware does. For example, if you want to multiply two 4096 by 4096 matrices, the resulting matrix will have 16.7 million cells. So we ask for 16.7 million workers, where each worker is assigned to calculate one of those cells. Each one of these workers is called a thread, loosely the same idea as the standard thread on your CPU. These threads are bundled into blocks before being sent to the card. Each block can hold up to 1024 threads. The blocks are then sent into the GigaThread engine at the bottom of the chip. The only job of this engine is to look across the 132 multiprocessor on the chip and send a block to each one of them that is free. And when a multiprocessor finishes executing one of these blocks, the engine gives it the next block in the line. Now let's look inside one of these blocks. The multiprocessors cut the threads into groups of 32. Each one of these groups is called a warp. Each warp goes to one of the 4 warp schedulers, and the scheduler puts each one of these 32 threads onto its own CUDA core. So every thread in the warp is running the same instruction at the same time, just with a different set of numbers. Now let's follow one of these threads. The job of one thread is to only calculate one cell, so it starts by asking for the first number of its row. But the thread is running on a CUDA core, and that core can't reach to the card's memory directly. It can only read and write from the registers, that is small blocks of storage inside its own multiprocessor. So the numbers of the row needs to first brought into these registers. The request leaves the multiprocessors, goes across the chip and arrives at the memory stack. The numbers are then pulled from the memory, travel back and land in a register. Now the thread has access to those numbers. It runs one multiply, one add and puts the result into a second register. That is only one pair out of 4096. So the thread repeats the same cycle again and again until the result of the cell is fully calculated. Then the cell is sent back to the card's memory. The entire multiply and add operation takes 4 clock cycles, but the trip out to the memory and back takes hundreds of clock cycles. Now all of the other 16.7 million threads running across 132 multiprocessors at the same time perform the same operation, and the resulting matrix is built in a memory. This matrix is not sent back to the host yet, because it's only the result of one layer of this neural network. The host launches the next kernel, and the same thing happens one layer after another. For example, in case of GPT-3, it has about 28,000 of these matrices stacked into 96 layers. So we need to do 96 rounds of this calculation before there is an answer. When we finally reach the last layer, the resulting matrix then trips back over the PCIe to the host, and then it gets translated into words and their probabilities. Then one word gets picked to appear on the screen, and that word also gets appended to the input text, and the whole thing is sent back down the interface, and every one of those kernels runs again for the next word. So now let's take a look at how one of these threads spent its time. The calculation itself inside the thread took 4 clock cycles, but getting the numbers across the chip from the high bandwidth memory to the thread took hundreds of clock cycles. And that's the problem here, what people call the memory bottleneck. These numbers sit on the memory chip next to the H100, so before a core can calculate anything, it has to ask for them. The numbers travel across the chip and land in the registers so the core can pick them up and do the calculation. Then the result has to be written back out, which means traveling across the chip again all the way to the memory. And then the next layer starts and we have to do the whole trip again. That's where those 100 clock cycles of moving numbers around add up. Now look at what each one of these cores is actually asking for. Remember that every cell of the result is independent. No cell needs the answer of another cell to be calculated, and that's still true. To do the calculation, the cell next to it needs the exact same row, the cell below it needs the exact same column. So the core sitting next to this one is crossing the whole chip to fetch the numbers that just arrived here, and the core below it is doing the same. Thousands of cores all making that 100 cycle trip for the numbers their neighbor has already fetched. So the question is, what if they didn't have to? What if one core took the number it just used and gave them to the core next to it, and that core to the next one, and so on? This way the numbers walk from one core to the next, and every core they pass through uses them once, and the memory across the chip is only accessed at the start and at the end of the calculation. And that's the idea a TPU is built on. We will take the TPU V5e, the chip Google built for serving models like this one. At the center of it is a single tensor core. Inside the tensor core are 4 matrix multiply units, or MXUs. Each MXU is a grid of multiply and add units, 128 units by 128 units. So there is 16,384 multiply and add units in one array, almost the same number as the CUDA cores on the H100, except here they are not independent. Each unit is connected directly to the units next to it with no memory in between. A number can only come into unit from a unit on its left or unit above it, and it can only leave the unit on its right or unit below it. On every clock cycle, each unit takes one number in, passes one number out, and does one multiply and add operation in between. A grid wide like this is called a systolic array, and the names come from the heart because the whole grid moves numbers on a beat. All 4 arrays together get through nearly 200 trillion multiply and add operations every second. Now let's zoom out and look at the rest of the chip. Right next to the arrays is a block of memory called vmem. This is where the numbers are kept right before the arrays to use them. That's the same idea as the shared memory inside the streaming multiprocessor, only much bigger. And outside the chip is a high bandwidth memory. This is where the parameters of model are loaded, the same as the card we opened. Now let's actually run a matrix multiplication on this. First, the weights are copied out of the high bandwidth memory into vmem. Then they're loaded into array, one number into each unit, and they stay there. Now the input numbers enter from the left edge. On every clock cycle, each number moves one unit to the right. When the number arrives at the unit multiplies it to the weight stored inside it. Then it takes the number coming down from the unit above, adds it, and passes the total down to unit below. So the input numbers move right along the rows and the total moves down the columns. When the total leaves the bottom of the grid, every unit in that column has added its part to it. And that's one finished cell of the result. The rest come out of the bottom edge right behind it, one after another. And while all of this happening, the next chunk of weights is already being copied into vmem, so the array never has to stop and wait for the memory. Now look at what didn't happen. Not one of these units asked the high bandwidth memory for anything. The weight was already inside the unit, and the input number came from the unit next to it. No number was written back out and read again between one multiply and the next. So the whole calculation reads and writes the memory twice. Almost all of the energy inside the array goes into math and almost none of it into moving numbers around. That means the less work with less electricity and the chips that's cheaper to build. So if a TPU does the same with the less electricity on cheaper silicon, why is still everyone buying GPU instead of building chips like this one? The answer is the same thing that makes them fast. A TPU is fast because it's rigid. The transistors are built to do one kind of a specific math. And right now that's exactly the math a transformer needs. But what happened to the data center full of these chips if somebody finds a better architecture than transformer next week? You're left with billions of dollars of silicon that can only do the math we use today. In contrast, a GPU never made that bet. If the math changes tomorrow, you rewrite the code and the same code runs it. That flexibility is what NVIDIA is really selling. But for now, let's wrap it up here. If you learned something from this, consider subscribing. I open up systems like this one piece by piece on this channel.